Welcome, everyone. Our speaker today is Liz Munch, who will be talking to us about bounding the mapper graph interleaving distance with a loss function. Take it away, Liz.
Hi, thanks. So first off, thank you to the organizers. I always love the AATRN and all of the wonderful online videos, and this has been really great. So thank you all for organizing and for having me come speak again. So I'm going to talk about something that we've been thinking about recently, and this is a talk that's going to be a bit more in the weeds. So I apologize. It's going to be relatively specific about some things we've been thinking about trying to make interleaving distance reasonable in any sort of practical context. So that's the main idea of what I'm trying to do here. So let me give a sort of, let's try to make sure my slides work. There we go. Okay. So big pictures, this is sort of what I see in terms of TDA related things in general. There's broadly two classes of topological signatures that we tend to have show up in practice. There's the sort of algebraic bucket of all of the things that come from probably something homology-based, Euler characteristics, persistent homology, Crocker plots, all these fun things. Today, I'm not going to talk about anything with that. Today, I'm going to talk all about graph-based signatures and sort of how to work with those more directly. So in particular, I've spent a lot of time thinking about things like the Reeb graph, right? So a Reeb graph where essentially the idea here is you have some sort of input information. Your input information is something like a topological space with some sort of function to R. And we're going to take that information and collapse it down into connected components based on level sets. So in this particular example, right, if I have a particular function value, I've got the level set, which here is probably something like 2 disks. And if I collapse down these connected components, I get these 2 different pieces on my Reeb graph. And if I build this manner, and if I have nice enough assumptions, restrictions on my inputs, I'm going to have some sort of graph looking signature. So the other thing I'm going to warn you is when I use the word graph, what I really mean is topological graph. I mean probably something closer to a one-dimensional stratified space. I mean, I have vertices, I have edges, but really my edges are sort of like copies of real line, of little intervals, right? So I want this to be a topological space where I can work with any point in the middle. So one of the things that's related to the Reeb graph is the mapper graph, right? So there's this version of something that looks very similar to a Reeb graph that shows up in practice a lot, which is maybe I don't have full information about my underlying topological space. Maybe I'm just trying to approximate anyway. And what I'm interested in is taking, rather than information about every single point and every single connected component of every single level set, I'm going to work with some cover of intervals. So here I've covered the real line with some intervals, and I've got some sort of input data, in this case, point cloud sampled from whatever interesting underlying manifold. And the game here is I'm still studying connected components and how they're related to each other, but I'm now doing it in a more discretized setting where I've either discretized the real line or I've discretized I've sampled my underlying space, or maybe both. And the result is still this sort of graph in a bit more of a combinatorial nature at this point, but still some sort of information related to my original input data and how my connected components are related to each other. All right, so when I talk about inputs for mapper in this particular talk, I'm going to go hardcore categorical input version of this. So let me tell you what I mean when I'm talking about the mapper graph information. All right, so my input data, as before, is still a function. I'm going to relax the assumption that it goes into R. This thing could go into RD for some bigger D. A lot of my pictures are going to be with D equal 2, but D equal 1 is probably the most common version that people will show in terms of mapper graph applications. The way I'm going to represent my data is I'm going to keep track of connected components and the information about how they're related to each other in a functor. So in this case, the way that we can come up with this mapper graph is by taking whatever cover you were interested in, right, nice enough or not. I can build the nerve of that cover, and I can consider open sets in the nerve of this cover. I'll explain what I mean by that in a little bit. But for any of these open sets, I could go back and say, all right, that open set in the cover, I can look at the geometric realization of this thing, so the union of all of the cover pieces. I can look at the inverse image under this function, and I can look at the connected components. So pi naught is the functor that spits out connected components for whatever your input topological space is. And of course, this is a functor. I didn't write down everything. So if you have some containment into B, then I've got some sort of, oops, that should be a B, right? So I've got all of this relationships between all of my composition or inclusion of sets. And so I've got all this additional structure that I can use. So if you're not comfortable with this version, you can sort of go back to thinking about this like a more traditional mapper graph. So here's my example for d equals 1. So I've got my input data, I've got my real line, and I've discretized it, and I've come up with some sort of nice cover, right? So all these different interval pieces that's covering my data. And essentially what I'm doing is over top of any of these pieces, I'm keeping track of connected components. So for, let's find one that's kind of interesting. Is that one interesting? Nah, let's look at this one. So for this particular interval, right, I can look at the connected components in the inverse image of this interval. So in this case, I've got sort of two pieces, this guy and maybe this guy. And so what I'm going to do if I want to represent this in more of a graph-based structure is I can keep track of this by having 2 points in f of that interval piece. And then what ends up happening is if you track all of this categorical structure and how these different sets relate to each other, you can keep track of these things in terms of the edges, right? So the edges are over top of, oh boy, this one's intersections, right? So over top of intersections. And so I can keep track of that information and how it relates to all the other pieces. And the result ends up still being something that looks like a graph, even though I'm storing it in this categorical framework. In the higher dimensional version, so again, I'm going to draw a lot of pictures for d equals 2. So now I've got data embedded into R2. A lot of times for these pictures, just because it's a bit more manageable in terms of controlling what these pictures look like. So we started this project by being interested in looking at embeddings of graphs, right? So in this case, I've got some sort of embedding of a graph in the plane, right? So there's one of my graphs. And I can look at connected components over top of some grid I've imposed on the structure. So now I'm living in R2. So what was a bunch of intervals over a grid now becomes these sort of grid-like pieces. And so what I can do is I can keep track of connected components over top of these grid pieces. I'm going to lose a bunch of the nuance, but again, I'm going to be okay with that because this is going to be some sort of approximation. But so for instance, the information over top of this particular open set that we're going to work with is some connected component, and I can track how that relates to things over top of this connected component and the piece on the side, et cetera. Okay. So this is what I mean when I'm talking about my input, because we're going to work with this categorical framework for representing mapper information, where really what I'm just doing is mathematical structure that stores connected components over top of the particular cover I'm interested in and the relationships between them, and sort of think about it as a graph when I want to compute anything, but think about it as a functor when I want to prove anything. Okay, so here's the goal of this talk. All right, so I'm interested in thinking about distances between mapper graphs. So what I mean by that is you give me 2 input mapper graphs, right? So this is my sort of Reeb graph, mapper graph, whatever version of this picture you want to think about. But the idea here is you give me 2 of these objects coming from whatever the heck. And I want to come up with some number that says something about how similar they are. So in this case, this should satisfy the general rules of a distance where it should be symmetric. We should have something that looks like a triangle inequality. And you should have small values and or 0 values. 0 values mean that you actually had the same input data. Small values should mean that they are similar in whatever sense I want to think about similar. Now, the trick here is I really also want to be able to compute anything, because the life goal here is to be able to take this, use any of this structure to talk about things where you're working with mapper graphs coming from real data. And so a lot of the things I've been thinking about in this particular realm have not satisfied that particular condition. And so using it in practice has not really been available. So to that end, the distance I'm going to think about, which is not the only option, but the distance I'm going to think about is the interleaving distance. All right, so first off, I'm going to apologize in advance because I'm sure I've missed people on this slide, and I've shown it several times. And so at this point, I'm hoping that the people that should yell at me have already yelled at me, but please yell at me if your name is not on here, and it should be. But the idea here is that the interleaving distance is this framework that's taken off in the last, I don't know how many years. But the idea is this categorical framework where if you sort of view it in these particular settings gives you a metric on lots of different inputs that we're interested in, right? So this started with looking at things with persistence modules, right? So the original definition, and has sort of morphed into all sorts of different cases where, depending on what sort of category you're interested in, you can end up with different sorts of topological structures and representations, and then you sort of poof magically get this distance on the things you want, right? So in persistence module land, right, I was interested in some sort of functor where you end up with information in vector spaces. The trick here is if we're going to think about things generally related to graph-like objects, you usually want to have functors that are looking like something that goes into set. So this is where we're thinking, is sort of these guys over here. All right, so the nice trick is I can just sort of pull all these ideas from the categorical representations. Because of the translatability, I get this distance between these objects. All right. So the other big piece that we're going to use for this particular talk is this really nice work by Michael Robinson that came out in 2020, where he was interested in sort of a different problem from what we were thinking about. He was actually interested in studying sheaves. So he was looking for a particular choice of a sheaf. He wanted to say, all right, you handed me a sheaf, how far am I from actually being able to get something that looks like a section? Or if you handed me one, you handed me a thing that kind of looks like it should almost have the structure of a section, but doesn't necessarily actually satisfy the ideas of a section. How far am I from actually being a section? And so the big idea that we're going to steal from him that I really like is we're going to set up a structure where, or what he did was he swapped out his set information with pseudometric spaces. And so he started looking at these things by saying, okay, so let's create a measurement by using the pseudometric space structure on each of the individual images for any open set and use that as our measurement tool. So what we're doing is going to be sort of inspired by rather than actually directly using it, but I really like this idea. And so this is where we got a lot of these pieces out of. Okay, so the plan. So let me give you the big picture plan of what we're going to do. The idea is you have some sort of data embedded into RD, right? So again, pictures in R2, but whatever is in RD. In order to make things computationally nice enough, I'm going to work with a discretization of RD. So I'm gonna fix a particular cover on here, and I'm going to encode all of my mapper information as a co-sheaf and use that to define an interleaving distance. All right, so that's our setup. That's what I actually want to be able to compute. So what we're going to do is the following. I'm going to start by assuming somebody handed me something that looks like an interleaving, but isn't actually an interleaving because they didn't promise me any of the commutativity conditions that I want. I'm going to build a particular loss function where if I can figure out what this loss function is, I can build you something that is actually an interleaving. And in doing so, if I can build you something that's actually an interleaving distance, or sorry, if I can build you something that's actually an interleaving, I'm going to be able to use that to bound the actual interleaving distance value. Right. So this is our goal. So this is the big bit up here is that we're going to have, like Michael Robinson stuff, right? We're going to have something that looks like it should be an interleaving, but isn't necessarily, and measure the quality of that thing for our inputs. Okay. I'm also going to point out, and I know Teresa said this already, but please feel free to stop me and get me to go explain things. And there's always a high chance of typos and things. So I'm happy to slow down and answer questions as necessary. Okay. So that being said, let's go set up all of our definitions. All right. The grid. All right. So here's what I want for my grid. Again, I've got my data, my original input data that I don't really get to see, but somebody's holding on to in the background. Is some sort of topological space with a map to RD. What I'm going to do is I'm going to take the image of that map, so the RD portion, and I'm going to discretize the space I'm interested in. So this is going to be K, which is going to be a cubical complex. I'm going to decide on some delta in advance. So I've got some sort of delta parameter that I'm interested in terms of sort of how fine my grid is. And of course, because this is a cubical complex, I get all my nice face relations, and I've got this beautiful, topological combinatorial structure. All right, so here's my picture when D is equal to 2. So this is my grid in the case that D is equal to 2. And so the idea here is I can hand you this cubical complex, but I need to be able to figure out what open sets mean in this particular context. So to do that, we're going to use what's called the Alexandrov topology. All right, so here's how you get a topological space out of this combinatorial structure. All right, so if you give me a subset of cells, so S in this particular definition is you just give me some pile of elements of K. So this could be squares, edges, vertices, combinations thereof. For the moment, I haven't actually controlled anything about that set. You just give me a subset of these objects. The upset of that set is the collection of other cells, which are upper adjacent faces of cells that are in the set. Okay, so in this particular example, so let's go to this example. So if my set consisted of just that vertex, the upset from this vertex includes all of those edges as well as the 4 additional squares. So this is a set of size 1, 2, 3, 4, 5, 6, 7, 8, 9 different objects, right? So combinatorially, just 9 different objects. You can similarly do the same thing that you want for downsets, right? So this is, if you give me a set, you give me all of the things that are lower adjacent to whatever my input data is. But for the purposes of this particular paper, we're going to focus on upsets being defined to be the open sets in our particular topology, right? So we build this entire structure by saying, all right, I've got all of these upsets, and I decree a set to be open if and only if it's the it is an upset. Right. So okay. So you can also set this up by looking at a basis of this particular topology. So the picture down here should sort of make you think about this anyway. But the idea here is that if you give me any cell in my original cubical complex and take its upset, I'm going to denote that as U sub sigma for any given sigma. That is a basis for this topology. So you can start thinking about these sort of pieces like this. So open sets look like the following. If you give me, okay, this is my D equals 2 picture. If you give me a square, nothing is upper adjacent to it, and so it is its own upset, so it is itself U sigma. If you give me an edge, the resulting upset is the collection of 3 objects you see there. If you give me a vertex, it's the collection of, what did I just say, 9 objects that you see there. All right, so this is my topology in this space that I'm going to work with. And then what we can do is define a thickening on this, right? So this is sort of leading into the fact that thickenings are what I need to be able to come up with interleavings in the next slide. So the thickening operation is you hand me some open set in this topology. I can define the n thickening as follows. All right, so if n is equal to 0, you just give me back the set and we're done. For anything higher, what I'm going to do is I'm going to take the downset and then the upset of the resulting downset. So I'm going to take whichever way the English language works, the upset of the downset, right? So you should end up with an upset. This thing should end up being itself an open set in my set. But what ends up happening with this is this sort of nice grid expansion structure that sort of intuitively makes sense when I use the word thickening. So for example, down here, I've shown the one thickening of all of these 3 different open sets. So my one thickening of this guy's U sub sigma is now the combinatorial object. I'm not going to count that, but that many combinatorial pieces put together is now U sub sigma 1, 1 for the one thickening, right? And so if I were to do the 2 thickening, I would just do this operation again. So in this case, if I did the 2 thickening of this guy, it would be take 1 grid element out for all of these pieces and then take all of those bits. All right. So the perk here, okay, so now I've got a grid on RD, I've got a topology on that grid, and I've got a way of thickening open sets in that grid. So what I'm going to do is use that to build my co-sheaf structure. All right, so on the previous slide, right, so I built what K was, open of K, so that's now my Alexandrov topology opens in this set. All of my open sets in here, I mean, combinatorially when I write it like this, I want to think about these things as being like discrete collections of these pieces. And then if I write the sort of absolute value looking things, this is, I mean, the geometric realization, the subset of the space. And so the idea here is I can store all of my mapper information by taking any open set over here and storing all the connected components over top of the geometric realization of the open set. All right, so for example, if my orange bit is my U, then my, okay, the way I'm going to write this is the points A and B are elements of some connected component, which I'm going to represent by capital A and capital B. right? So my connected components in f of u are two different objects, a and b. If I do the same thing for v, which is supposed to be this bigger guy out here, right? So I should have three different connected components. This thing, the big guy, and then this guy is off by himself, right? And the trick here is that because I have a co-sheaf structure, I know that if u is included into v, I get maps induced on the underlying sets. So the connected component A maps to the connected component I'm going to write down as A prime, where all I mean here is the point A is the connected component in f of u, that includes the point A. A prime is the connected component in v that includes the point A. Okay, in those cases, that's kind of boring because they're the same, but the B one is a bit more interesting because B's connected component starts as being that thing, and then B prime means the whole big connected component that's still attached to B there. Okay, so I've got all of this structure. And again, this is sort of magically encoding all of this combinatorial information that I want. All right, so I can build an interleaving distance. So again, if you've sort of seen any of this literature, this should look very similar to all the other versions that you've seen, some minor changes just for our particular input. But I've got two input co-sheaves, so those things are currently representing my mapper graphs. I'm going to fix some n greater than 0, and then or greater than or equal to 0, and an n interleaving is the following. I need a pair of natural transformations, phi and psi, that go from one to the other precomposed with this thickening, and the first to the other, whatever, precomposed with the thickening, right? So this is just supposed to mean if you're looking at the map that goes from f of u to g n of u, so this is thicken your open set by n, and then look for maps that go into that thing, right? So I need to have natural transformations, and I need to make sure that these triangles commute. So these triangles are essentially making sure that I would like these things to commute with each other in as much as that makes sense, right? So in particular, if you set n equal to 0, this is me telling you that they need to be naturally isomorphic, and greater than 0 is essentially giving me flexibility to find these maps. Okay, so my interleaving happens when I fix some sort of n and I find a pair of these things. So the interleaving distance is the smallest possible n for which I have a pair of these maps. Right? So the game is, tell me the minimum n where interleavings exist, right? So in particular, if I give you an n interleaving, that at least gives me an upper bound for what the true interleaving distance is. But we're going to be interested in trying to find something as low as possible. Okay. All right, so with that, let's try to figure out how to compute this thing, or at least what we're actually going to do is bound this thing. All right, so the loss function. So here's what we're going to do in order to come up with something that I can control the interleaving distance with. All right, we're going to build something that we're going to call an n assignment. So an n assignment is, okay, sorry, let me back up. An unnatural transformation is a collection of maps where if I had an additional commutativity assumption, if I had a pile of maps for which this square always commuted, then I could promise you that it was a natural transformation, right? So I'm going to give you all of the data you need to build a natural transformation, but not promise you that it actually commutes. That's an unnatural transformation. If I put a pair of these two things together, then that's called an n assignment. So an n assignment is a pair of unnatural transformations that look like they're heading towards being an interleaving, but I have not promised you anything about anything commuting, right? All right. Now, I'm going to point out, this is horrific use of the English language. So an unnatural transformation, or sorry, wait, no, let me say that backwards. A natural transformation is an unnatural transformation that happens to commute. Okay. Don't blame me for this terminology. We found this on NCAT lab, and so I'm sticking with it, but it does not make any sense, and I'm very sorry. Anyway, we're going to talk about assignments for the most part anyway. So assignment, the way to think about this is I'm going to give you an n assignment, and that's going to be structure that almost looks like an interleaving without any promises. Okay. if I have this n assignment, and if it actually does what I want it to do, which is that it actually gives me an interleaving, then I have all of these diagrams commuting. All right, so what are all these beasts? The first thing I have to check is to make sure that whatever my pair of input diagrams is actually forms an interleaving, right? So this is the taking the un out of the unnatural transformation bit. So I would have to go double check that every diagram that looks like this and every diagram that looks like this commute to make sure that both of these things are natural transformations. And then to make sure it's an interleaving, I got to make sure that all of the triangles that look like these two things also commute. All right, so if I hand you an n assignment and I want to make sure it's an interleaving, I got to go check all diagrams, all possible diagrams of this form to make sure that they commute. Okay, so here's where we're going to put a distance on these things. So here's the idea. If you fix one of these open sets, okay, so I can look at f of u, that's the set of connected components over top of the set u. What I can do is I can define a distance on elements of that set where I'm going to go look for the smallest possible k for which under this thickening, those two elements get mapped to the same thing. Right, so that's what this notation is supposed to say. So this is the map that sends f of u to f of uk. So this is the basically saying how small can k be before these two objects are in the same place. All right, so for my particular example here, let's look at the WZ ones, right? So I've got f of v in this particular example. I've got two different connected components, and I need to thicken twice. So thickening once, they're not in the same connected component, but thickening twice, they are in the same connected component. So now I've got this distance defined on the two objects of f of v. Similarly, I've got a distance defined on the objects of f of u, so a and b. In this case, they're not in the same connected component, but they are after you expand by 1. Okay, so there's the distance that I've come up with. Excuse me. All right, so my loss function is going to be measuring how far those diagrams that I wanted to have commute, how far I would need to expand them before they do actually commute. So let me explain what I mean by that. So let's look at the natural transformation version first, right? So I really want that diagram to commute, but nobody promised me that, so I can't deal with it. Instead, what I can do is I can say, all right, let's fix some object up here and see where it goes along this map, right? So by the time it got to the 2 points at this location, right, they weren't necessarily the same. However, if I look at this distance, I can promise you that wherever they were, they should go to the same point by this k. So if I thicken additionally by k, this diagram, while the left side doesn't necessarily commute, I end up in the same place by the end, okay? So that's what I mean by this L sub parallelogram UV. So the idea here with this notation is supposed to be U and V were the chosen open sets for these beasts. Parallelogram is supposed to denote the fact that I'm doing the parallelogram version of this, and phi is the only unnatural transformation involved. So similarly, I can come up with a measurement of quality for my triangle version, right? So this is the triangle diagram that I really want to have commute. I can go pick any object in here and kind of see where it goes under these two different directions. I can't promise you it's the same place in here, but the way that I've rigged this distance choice, whatever my k is, by the time I get out here, they're going to be in the same connected component mapped to the same thing. Those are equivalent in this place. Okay. So I've got these loss functions. All right, so now I've defined it for a parallelogram version and a triangle version. And so then the game is, oh, nope, sorry. We'll put that together in a second. Let me do an example. Right, so here's the computation of the loss function for the parallelogram bit. So the first one on the previous slide. All right, so the idea here is that if I'm interested in checking whether or not hold on. I'm going to be checking individual objects in each of these sets. Let me come back up to that picture in a second. All right, I can compute all of my distances for all of my objects. So this is just supposed to be me checking all of that information, and hopefully my picture matches up. Somebody in the ether handed me an n assignment. So this is all of the map data that somebody else passed to me. And so then if I want to go check my loss function, I can go try to see where different things land. Okay, so in particular, let's look at the object z. So Z represents the connected component in G of U, which is just this bit right here. If I map it to G of U1, sorry, we're doing a 1 thickening here. If I map it to G of U1, that's still some connected component, and that map is given to me. However, these maps were decided based on whatever this N assignment was that somebody else handed me. So in this case, Z maps to A prime according to, where's that guy? This particular map. Z prime maps to B double prime under this other particular map. And so if I chase these pieces around, I get to 2 different objects, right? So starting from the same thing, I get to 2 different objects, but the distance between A prime and B prime is 1 because if I thicken one more time, then everybody's in the same place. All right, so in this particular example, this parallelogram part of the loss function, this is 1. Okay, so let's put it all together. So the definition of the full loss function is you give me some N assignment. We're going to define, all right, we got to do the symmetric version. So we're going to end up with 4 different bits of this loss function. So I'm going to end up with 2 versions of that parallelogram loss function. And I'm going to end up with 2 versions of this triangle loss function. So I'm going to put all this together. So the loss for a particular given N assignment is the maximum of these 4 numbers. All right. Cool. All right. So if the notation is gross, but this is just what's the minimum K so that everything commutes by the time you get out to that K. Okay, so I've got this loss function, and it's basically set up in such a way that it's nearly immediate to prove this bound. All right, so you handed me an N assignment. Again, the N is sort of provided data that comes with the fact that the original assignment was an N assignment. I compute this loss function for you, and then I can promise you that the interleaving distance between the 2 inputs is at most N plus this loss function. Okay. So in particular, the proof is really based on building the actual interleaving that you want. So again, if you give me some N assignment that I had no control over, and you can tell me that the loss is K, what I can do is I can build for you an N plus K assignment by just composing the things that sort of make sense. So you handed me phi and psi. I hand you back capital phi and capital psi for all possible open sets that I want. And the rest of the proof is just make sure that everything that you wanted to have commutes because you can sort of shift over to this K shifted version of everything. All right. Okay. So, right, this is lovely, but computationally not particularly great. And specifically, if you give me every open set in this grid, right? So open sets are now combinatorial objects, but it's basically going to be every subset of varying size, disconnected components, all kinds of different things. We're going to have exponential numbers of subsets of my grid, and I really don't want to do that. Okay. So what we're going to do is we're going to get ourselves down into a bit of a more manageable, under control list of sets to actually check to figure out what this loss function is and still bound my interleaving distance. Okay, so let's do this with a basis instead. All right. What I'm going to do is I'm going to modify all of my definitions. Instead of an unnatural transformation, I'm going to be interested in basis unnatural transformations, where really what I mean is you just have to hand me a list of stuff over top of these basis open sets, right? So you could have handed me more open set information, and I don't particularly care because I'm going to ignore it in about a slide. But you're at least telling me for every possible cell in my grid structure, you're going to tell me what all these maps are, and that's it. And again, no promises about anything, but you just handed me a pile of these maps. Similarly, if I put 2 of these together and I happen to have all of this information, but only on open sets, then putting those together, we're going to have this basis and assignment instead. Okay. So we still have these diagrams we have to go running around and checking, but in particular, I'm going to be interested in diagrams that are only involved with basis open sets, right? So the bottom one is honestly the easiest version because now instead of U from before, I just have U sigma wherever you can see it. The top, your open sets, you're just going to be interested in pairs of basis open sets in particular. So if tau is your, which way do I want this to do? If tau is a vertex and sigma is an edge, then you have this map on inclusions. And similarly, I'm going to look at sort of pairs of these maps where I'm only interested in basis open pairs of these sets. Okay, so if you put all that beast together, you get a new version of the loss function, which looks super similar to the thing before, except that suddenly all I'm interested in my loss function is checking the k values for that, how far out do you have to go before you commute, for this particular list of sets that are only the basis or pairs of basis opens. All right. So if you have that, it turns out that everything still works, right? So if you give me a basis and assignment, I can still get this basis loss function bound that looks similar to the other one. Right now, what's really nice though is that this beast is polynomial time to compute, because suddenly I have a fixed list of either elements of k or pairs of elements of k. And I have to check a bunch of these open sets and figure out what this k is, but it turns into just checking a whole lot of connected components and how they're related to each other. Okay, so how bad am I doing on time? Not too bad. Okay. So let me give you sort of a general idea of what we just did, and then talk about how this thing is useful in sort of a bigger context. All right, so what did we do? So somebody handed me two mapper graphs they wanted to compare. So F and G are input data to start with that I don't get to control. Somebody gave me an N assignment that I also do not control, where I can go running around trying to figure out what the loss function value is, or my basis loss function in particular, for this particular choice of N assignments. And what I can do is I can, on top of that, when I'm building all of these things, I can provide for you an explicit N plus your loss function shifted interleaving phi and psi. So we're going to get an interleaving, and so that sort of automatically gets you your bounds. All right, let me tell you what we did not do. What we did not do was tell you anything about how good this bound is, right? So somebody out in the ether handed me this N assignment, and how good the bound is entirely dependent on how good that input was and whether or not it was getting anywhere close to a reasonable option, right? We didn't show anything about tightness. We didn't say anything about how good a job we're doing at all, right? But the idea here is supposed to be somebody else has handed me all of this N assignment information, and I can get a bound, and then maybe I can use that as some sort of method for improvement. Right, so the sort of big goal version of this that we're currently working on is the following. You give me some sort of arbitrary phi and psi N assignment starting case. I can compute this loss function. Sorry, those should be the basis versions, but whatever. I can compute this loss function. And now maybe what I can do is try to improve my assignments in order to get you a better loss function and therefore get you a better bound, right? So in particular, we think this fits into sort of a nice gradient descent-ish style model where you can actually start updating these things. And because I've got some combinatorial control over these beasts, I can actually start getting to some sort of reasonable bound on whatever's going on. The other thing that's really nice about this particular framework, in my opinion, I'm using all of my pictures in terms of these mapper graph things, but everything I defined was very categorical, right? So the distance function in particular is entirely based on finding a value of thickening for which two things end up mapping to the same place, right? And I'm thinking about it in terms of connected components, but those could be sort of other ways of thinking about mapping to the same place. So in particular, I think there's ways of taking these ideas and using them for things like multi-parameter persistence interleavings, where sort of we got a different sort of way of talking about things being the same, but there's potentially interesting things to do with that. The other thing that I'm interested in working on is how do you take this information and extend it to Reeb graphs, right? So this is sort of like the more exact version of the value that I actually want, right? So I think that this can be extended with enough careful bookkeeping to Reeb graphs to get an exact answer. But let me tell you how to do it to get a approximation rather than an exact answer. All right, so let me just take a little bit of a divergence and talk about Reeb graphs for a second. All right, so Reeb graphs are very similar in flavor to everything I just talked about, except for the fact that what I'm going to do is I'm going to keep track of information over every possible, okay, I'm going to do this with d = 1, every possible interval in the real numbers, and keep a similar idea, right? So for your interval, you're going to keep track of connected components and they relate to each other, and isn't that great? I similarly have a thickening operation where I can take an interval and I can thicken it. AB goes to AB thickened by epsilon. An interleaving is a pair of natural transformations for which, I'm not going to write it again, but all of the diagrams that we had from before commute. And then my distance is the smallest possible epsilon for which there exists an interleaving. So, like I said, I think this framework has the potential to work in the exact answer case. But let me use this to get an approximate bound for my Reeb graph interleaving distance. All right, so you give me 2 input starting structures. I'm going to fix some delta to come up with my grid, and I can either build my mapper graph version or my Reeb graph version of my categorical representations of these objects. So the first thing that you can check is that the Reeb graph version of this distance is upper bounded by your mapper graph version of this distance +1, and there's a times delta because everything I did with the mapper graph version was just sort of this integer indexed, but now this delta is sort of controlling by the fact that thickening by 1 grid element is related to thickening by delta in the real line. And if you give me some sort of basis n assignment for my mapper graph information, what that does is it tells me that I can figure out what the bound is for those things, and then promise you that your Reeb graph interleaving distance is upper bounded by this thing I can figure out, which is just n came with my input data. This is the basis loss function I came up with. 1 comes from this 1, and then I've got my delta out in front. Right. So in particular, I think there's a lot of potential for using this to have a nice way of coming up with bounds on computing or ways of computing or approximating the Reeb graph interleaving distance by essentially just deciding on how good of a grid structure you want to impose on it and go from there. All right. So with that, let me just thank my collaborators for starters. So Erin, Bay, and Sarah. So the other person that I want to point out, and I didn't get a chance to talk about her stuff yet, but Ashika up here is working on implementing all of this. And so we're hoping to have implementations posted very soon. This particular paper is posted on the archive, and I just submitted an update with all the Reeb graph stuff yesterday. So that may or may not be posted on the archive yet, but should be there soon. And so with that, let me thank you for your time and attention.
Thank you very much. That was a really nice talk. So let's all unmute ourselves so that we can clap together. And let's go into the question part. Does anyone already have a question? Maybe I would just start with one while people are still... No, Chunin, you can already go ahead.
Hi, Liz. It was a very nice talk. So I wonder if you have any idea how to come up with your n assignments in the first place. That's interesting.
That is a great question. Okay, so I've got 2 approximate ideas, and you know, one of them is this is we're going to call this the Bay method. So the Bay method is you do something very intelligent where you actually try to figure out, you have a lot of information. So let's assume you've got a lot of starting information about your embeddings, right? So I've got 2 different embeddings. Again, I'm going to think about this. We were thinking about embedded graphs, right? So I've got 2 graphs embedded into the plane, and I can go do some intelligent things by saying, oh, well, this connected component over here should probably map to the closest thing geometrically, right? So I've got this additional geometric embedding information that I can use. And so that seems like a super reasonable starting place, right? So I can use that as my sort of easiest way to come up with a mapping by like assuming I have additional geometric structure. I'm going to use the additional geometric structure. The naive way is honestly just, okay, let's just map things to random things, right? And so in all honesty, that's what Ashika's code is doing right now. And granted, we're doing this on very simple input starting data, but it's working really well. So the sort of naive, unintelligent manner seems to be fine, but I'm going to guess that if you're working with much larger data sets with much more structure, starting from something intelligently chosen is going to do better in general. What I don't know yet is exactly what sort of the information in this loss function is going to look like, because my other guess is that, you know, if we're going to do some sort of gradient descent thing, you could sort of get stuck in local minima just because you happen to choose something that was intelligent, but might end up getting you into some local minima. So I don't know exactly what that behavior is going to do yet, but we're still exploring how that's going to work. Thanks.
Thank you. I think that answers the question. Any more questions? And maybe I will ask one myself. Namely, this loss that you compute just with the basis elements, is it equal to the loss to the LB, and is it equal to the L, or
no?
is it
And
just
it's better, which is weird. Sorry, I got excited because I cut you off, but no. So I realized halfway through the slide that I didn't have. I've got a previous version of the slide where I actually go into that more concretely. Let me attempt to write this down. Never do math in public, but we're going to find out. So first thing is, so the basis loss function, if you give me a phi and psi, is actually less than the loss function. If you gave me a full n assignment, this is going to be, well, what are you doing? This is going to be the loss function I compute on the basis elements is a subset of the loss function I compute on the full set of open sets, right?
Yes.
And so intuitively, there's no reason why this should make sense, right? So why is it that I'm computing on a smaller set of things, getting a lower bound and still getting my my bound on my interleaving distance? So the answer is because if you compute this loss function on the basis elements, what you're doing is you're actually going to take information about the maps, the pieces that are on the basis elements, and then using that to extend to maps on the full set, where you're basically going to do a better job, potentially, at least no worse of a job, taking your information from all of the f of u sigma that you take as a union to get you your f of u, and then intelligently choose the map from f of u based on those pieces, right? So what ends up happening is, essentially, I wasn't allowed to screw up things as much, because I didn't necessarily do dumb things mapping for the big f of u pieces to other places. Like me on the proof side, I'm going to take the basis elements and then give you what the correct or the most reasonable answer for that f of u should have been. Does that make sense?
Yeah, so it's kind of that if the input does it badly by not extending in a meaningful way from basis elements to other things, then you can't correct for that later if you're kind of bound to use that. Okay.
Yeah,
cool.
That's exactly
Thanks.
Right.
Okay, then a question from Nikki Sanderson, please.
Hi, Liz. Great talk. Can you hear me? Yeah. Okay, cool. So I feel like just to kind of like summarize the ideas that I took away from it, like you're looking for this quantifiable thickening where things get mapped to like the same thing. And for you, the same thing means connected component. So if there was like any weirdness in how you do your thickening, like if you have those like non-basis elements, you could have really weird topology of it, but you don't care because you're looking for something really nice at the end. Is there some set? Oh, sorry.
No, go ahead. I cut you off.
Is there, and then you mentioned like, oh, you could look for other things other than the connectedness of the components, like once you do this thickening. Are there any like concerns you would have, or just like, you know, things to think about when it's like you put a new property instead of connectedness in terms of like what you might need to care about with how you thicken and what could happen there?
Yeah, so I think the place where I still need to think about this much more carefully is, in particular, where's my let me find my distance definition. So my distance definition, I am using I'm leaning very hard on the fact that I've got this set of objects, right? And I've got a set of objects where I'm going to go check whether the set of objects are in the same place. So in particular, what I'd like to be able to do is use this idea for vector spaces. but there's sort of a difference between thinking about vector spaces in terms of their basis elements and thinking about vector spaces in terms of the set of all vectors in the vector space, right? And so the sort of immediate extension to the vector spaces is sort of dealing with that difference. But then in particular, right, what you're interested in is things like, okay, so if I've got, if we're going to do multi-parameter persistence or something like that, right, I'm going to keep track of, rather than two things being in the same connected component, I'm going to keep track of whether or not two things are homologous. And so if I can track where those things go, then I can try to keep track of that information as some like, what's the smallest k to make. Basically, I mean, the whole thing is what's the smallest k to make all of the diagrams I need to have commute, right? And so it's commute up to homology classes matching up as opposed to connected components matching up. Does that make sense?
Yeah, awesome. Thank you.
Great. And we have a question in the chat that I will read out. Thanks for the talk. How might one start to think about minimizing the loss? Any progress towards optimizing the loss function in this particular project or others?
Yep. Yeah. So this is the sort of the current work that Ashika is up to right now. And so the idea is essentially trying to figure out, you now have these structures where you've got families of these maps mapping from one place to the other. And it turns out, I didn't actually end up making slides for all of this, but everything that I've just said in a categorical framework turns into queries of your data structures asking for, I've got two things over here, I figure out where they map to, are they in the same connected component of this sliced graph of this thing I'm representing, right? So the thing we're currently investigating is exactly your question. How do I update these maps in a way that improves the loss function, right? So in particular, I can take one of these maps and say, okay, so I've got, where's my example for, do I have an example for one of these? I'm trying to, whatever. Maybe I've got one of these maps that sends A and B to A prime and B prime over here. If I swap one of those pieces, if I send A to B prime instead of to A like it was at before, does that improve things? The problem is it affects a whole bunch of diagrams that you've got to go double check, right? And so improving one of your diagrams loss function could make somebody else's loss function go up. And so that's what we're still trying to sort of control and manage and figure out how to actually optimize. So keep an eye on what we're doing, because I think Ashika is going to figure it out. I think she's online too, so.
And maybe a follow-up question of that from me. Like, is it somehow differentiable or so? Can you somehow compute some
not
optimal
really.
direction?
So I'm using gradient descent in sort of the heuristic manner. So this would be more like oh, my brain, Markov chain Monte Carlo, some sort of like combinatorial updates, trying to figure out like sort of combinatorial updates and whether or not they're improving anything locally.
Okay, cool. Then Daniel Tolosa, please.
Yeah, hi Liz, thank you for the talk. So it seems that I just want to check that your proofs don't use anything about the fact that you're working specifically with connected components, right? It's purely categorical, right?
Yep. Yeah,
Okay.
and so like the
Okay.
first version of this paper, if you go back on our archive history, the first version of this paper, we didn't realize that yet. So the first version was like, okay, we've got this map, we've got these graph inputs, and we were specifically looking at these things, and we're defining this, particular structure. And then, yeah, the further along we got, the more we realized that like, it's sort of an accident that I'm thinking about these things related to this geometric input information. But yeah, everything in this distance in particular, this is some sort of functor that you passed me. I've got no control over, or I'm not using anything from my original input to say anything about it. So yeah, so there's no reason why you couldn't define this on just from here, arbitrary set valued functors that you got from wherever, and you want to compute this distance. Yep, there's no geometric information whatsoever. I mean, the places where the geometric information is potentially helpful, so as mentioned before, like intelligent starting choices for your N assignments is one place. And then trying to sort of go back and use the information from before. We were originally thinking that you would have some sort of computational structure that had to do with like shortest paths in the graph and things like that, but we didn't end up doing any of that. It's really just 100% looking at the functor structure.
Yeah, so that kind of ties to the next question that I had. You brought, like, at some point in the talk, you mentioned something about how you wanted, you cared about having a metric on your grid here, but I didn't really see where you use that.
Oh, are you talking about why I'm trying to get an open set? Let's see. So back here, so one of the first things I have to do is deal with open subsets. Is this what you're talking about?
Well, not really. You mentioned the work of some other paper that was in 2020, and
Robinson's paper, yeah.
yes, that kind of like didn't work over sets, but
Oh yeah. So in this case, so he was just doing something completely, completely different. He was interested in a different sort of question. So he had a single input he was doing sheaves, a single input sheaf, right? And so in order to do anything with sheaves, I got to know what open sets are, right? So I've got open sets, and he was interested in rather than trying to build anything with an interleaving, right? So his question was, you give me something that kind of looks like a section. So in this case, an element from every open set for which all of the things that need to commute do commute, or that would be a section. If I can't promise you commutativity, then it's not necessarily a section. But what he was doing was he was putting a pseudometric structure on each of his sets. So for every U, I've got a P of U, and then he sticks a metric structure on that thing. And he uses that metric structure as his measurement tool for, if you hand me a section, how good a job or how far am I from actually getting something that's what I actually want. So yeah, we spent a bunch of time. Like I thought at first that everything we were doing was actually going to fit into his framework, and I couldn't figure out how to make that work. So it's just sort of a moral inspiration as opposed to a direct application.
I see. Now it makes sense. Yeah, it's more of like an analogy of how you're it doesn't commute perfectly, but then you look for when it does, and that's your assumption. Okay, I got it. Thank you.
Great, thank you to everyone who asked the question. We had some great discussion. Maybe let me end the recording here, and thank you again for this great talk.